now, I'm actually working half of my time here at the CWI, and the other half of my time I work on real-world problems on the psychiatry department, actually, of the UMC Utrecht. But today I will be telling you more about the theoretical part of my work that I performed together with Peter Grunwald, and his name is also on the slides because he made them together with me, and he's sitting here in the front row, so he's also available for answering your questions at the end. Yeah, so the goal of our project was quite broad. It was to develop tests that can be used under optional stopping. So Christina already explained this scenario to you very nicely in her talk. So we collect this data, and during our data collection, we want to say, okay, our new strategy is better than our old strategy. And we also want to do this in our project with the notion of effect size. So ideally, the thing that we want to end up with is the figure that you see here. We collect data, and at the start of data collection, we have no idea of the range between which the effect size really is. And while we collect the data, our estimate becomes narrower and narrower. So that's our ultimate goal. So today, first, I will show you a practical example of a sequential test setting and how we can improve upon just doing one hypothesis test in such a scenario. Thereafter, I'll give you a short overview of the setup we're working within with our methods. They are very flexible, but there are some constraints. And I'll explain to you the running example that we'll use throughout this presentation. Then I'll first show you the slightly easier problem of just A/B testing in our sequential setup. And then we'll extend it to the estimation problem, where we want to develop these anytime valid confidence intervals. So first, an example to get you interested in the problem. So something we analyzed for one of the first papers we wrote was something that really happened, the Swedish study on stillbirth. So this was a Swedish study where they wanted to compare two strategies of managing pregnancies, inducing labor at 41 weeks or at 42 weeks. And it was not clear to them what was better. Inducing labor can cause complications, but waiting too long also can cause complications. And luckily, they had a safety monitoring board, because it turned out that in the 42-week group, there were unexpectedly many more deaths than in the 41-week group. So they didn't observe any deaths in the 41-week group and 6 in the 42-week group. This happened after observing about 1,380 births in each group. And this was before they reached the point of which they said before they started the study, okay, then we're going to stop and analyze, because then we want to calculate our p-value, and then we have the power that we want. But anyway, they decided to stop, and they reported the p-value anyway. However, as we just saw in Christina's slides, which are very nice, then you have this problem that if you look multiple times, or if you look at the time that you didn't plan and calculate your p-value, you lose this guarantee of your false positive rate, often called type 1 error rate in medical research. So it's very difficult to interpret this result of this study, but has it been performed for nothing now? So in this kind of situation, this is where you really sequential tests can help. And we were curious, would our sequential test, which I'm going to give you all the details of later, would this have helped in this scenario? And what we see is that with the standard version of our test, we would often have stopped earlier before this point in time. So certainly a useful topic to research, I think. Okay, so what is actually the setup that we're going to look at? We want to have a sequential setting where we can do optional stopping that is also flexible. So for example, something we could have is that the data come in a stream of balanced data blocks. So in this scenario, the research would be allowed to calculate a test result after each block of paired data has come in. But what you can also do with our method is you can say, okay, I have an unbalanced design. I expect to show the nice new website to twice as many customers as the old version. So that's also allowed. This is often a setting that occurs in the medical research as well, where we have a case control design with 2 controls and 1 case. And you can even do something completely crazy like this. And this is okay in our setup as long as we lock in the composition of the next block that we're going to analyze before we start collecting it. And so we denote this as NA and NB, the number of observations in each block, and we should fix NA and NB before we start collecting the data for that block. And it's good to choose this NA and NB as small as possible. Okay, so this is our setting. And so this setting with these 2 data streams and blocks is something that we have developed quite a general method for, but throughout this presentation, to be able to give you some examples, we'll be using a 2x2 contingency table setting. So you're probably all familiar with this, but just to be completely clear, we have 2 strategies, A and B, and we want to know if the success probabilities differ between these strategies. And under our null hypothesis, the observations Y, which you can take on value 0 and failure, and value 1, which represents success, are independent of the strategy we choose. So probabilistically, we can say that our observations follow a Bernoulli distribution with a certain probability of success. And then under the null hypothesis, these success probabilities are the same. So the following figure always helps me to think about this problem. And I will also let it come back a few times in the presentation. So somewhere in this unit square, the true success probabilities for both groups lie. So on the x-axis, we have all possible success probabilities for the control group. And on the y-axis, we have all possible probabilities for the intervention group or for the new strategy. So what we're first going to do with testing is testing if the success probabilities differ. So if the real point, the real data generating distribution lies somewhere outside of this dashed line. And what we're going to do thereafter is try if we can estimate where the real point lies, for example, with the confidence interval. And then we can hopefully say somewhere in the shaded area, the true distribution lies. Okay, so this is our setting. So we want to do this sequential research, and the tool that we propose to use for this, or that we choose to use, are E-variables. E-variables have been around for a long time, I think since the 1960s already, but recently they've had a surprising revival, and several research groups among these 3, among others, have been working on them apart from each other at the same time. And yeah, maybe it is because we have this replication crisis of research that people got interested in this again, and research blew up. And what's really nice about E-variables is that the concept is very elegant and simple, easy to understand, perhaps even more easy than p-values. So E-variables are all non-negative random variables, so functions of the data, where under the null hypothesis, so when the strategies are not different in effect, we expect them to have a value of at most 1. So this is very simple, and it also has a very nice interpretation in terms of betting, which was mainly introduced by Glenn Schaefer, who wrote a really nice paper about this. So we can see this as when I do my study, I place a bet of €1 on my null hypothesis, and when the null hypothesis is true, I expect to lose my I expect to lose my bet. So over time, when I repeat this, I expect my money to perhaps even evaporate. You can compare this to going to a casino. The house always wins. You expect to lose your money. On the other hand, when I make an unexpectedly high profit, the alternative hypothesis might be true, and I might be able to reject the null hypothesis. And this always connects to the straightforward implementation in hypothesis tests of the E-variables. We can use them for a test and reject the null hypothesis if we see an E-variable that exceeds a certain threshold in value. So when we choose this value as 1 divided by a certain alpha, we have a type 1 error guarantee, or as Christina said, a false positive rate guarantee at level alpha. What you often see in practice is that people set alpha to 0.05, or I think in psychology today, even 0.01, and they reject. Then we would reject the null hypothesis if the E variable exceeds 20 or 100 in the 0.01 case. So this is a relatively broad definition, and you might think, well, what do these random variables look like? And here I have for you the definition of the very general expression that we found. So what you see here is an E variable that you can in general use for analyzing a point alternative in 2 data streams. For the null hypothesis, that the success probabilities in the 2 data streams are the same. So this might look a bit complicated, but it is relatively simple compared to many other E variables. So what we simply have is we multiply the likelihood of all observations that we've made under strategy A by the likelihood of all observations that we made under strategy B. And we divide them by another likelihood. And the parameter for this distribution, we have to choose in a special way. You can see here. So it's a weighted mean of the parameters of our point alternative hypothesis. And if we choose it this way, we have we have this property, and thus we have an E variable that we can use with this type 1 error guarantee. I have to say this expression holds for convex null hypotheses. And if you want to see the expression for non-convex null hypotheses, you can look in our paper. It's only slightly different. Okay, so we have this very general expression. But yeah, this is just for the analysis of 1 block of data, as you can see here. And now comes really the key point of doing an analysis with E variables. We can namely very easily convert them to an E process. So a very nice property of the E values is that multiplying them yields another E value. So this is really, yeah, some kind of magic. When we collect 3 data blocks, we can simply multiply the E value of each data block. And then we have a total E value that we can use to do a hypothesis test. And this really holds true for all moments in the stream. So we can do this at each moment in the data stream, at each data block. And then for any stopping rule that we want to use, for example, the E value exceeds a certain threshold, but we can also say, okay, we just stop when we have no money to continue our experiment. And then, yeah, we always have this type 1 error guarantee. So under the null hypothesis, the probability that there is any moment in the data stream that I reject my null hypothesis is bounded by our type 1 error. Okay, so that's very nice. We now have, yeah, tackled the sequential aspect, or the optional stopping aspect of our problem. One thing that you might think of, okay, you here talk about a point alternative, but yeah, you just showed us the entire unit square that we have to solve for the Bernoulli case. So what we propose to do there is to learn this parameter, estimate it, and plug it in based on the sequential data that we've seen so far. And we've tried out many methods for this. And you can even restrict the search space in this unit square by incorporating expert knowledge. And you can look in our paper from 2021 if you want to see the comparison between all these methods, which you can really improve upon power of the test if you do this. So what would this look like? When we have our first data block, we haven't seen any data before, so we just have to start with an estimate of theta A and theta B of 0.5, 0.5. And then as the data come in, we move closer and closer, hopefully, to the real data generating distribution. And a key point is, this doesn't change the null hypothesis that we're testing with our E variable. So no matter how we learn theta A, theta B, no matter how wrong we are, this does not interfere with our type 1 error guarantee. The E variable is still an E variable for testing the same null hypothesis. So I already touched upon power a bit. So you probably already saw this definition of E variables is very broad, all random variables that are non-negative and have an expected value of at most 1 under the null. I can think of lots of stupid examples. And this is why Peter and Wouter, who is also present, and Rianne, who is not here today, introduced the GROW criterion in 2019. So this stands for growth rate optimal, and they propose to design E variables that in sequential experiments would optimize the growth rate of your capital. So when you see this again as a betting experiment, we want to use the E variable that lets our profit grow the fastest over multiple experiments. And this is exactly the setting that we're using with the data blocks and the sequential tests. And this, of course, is closely connected to optimizing power, because as our capital grows quicker and quicker, we probably reject the null hypothesis quicker under the alternative. Okay, yeah, so that one important thing. We actually found that for the Bernoulli case, the general E variable that we propose is this GROW E variable. And so if we can learn the true data generating distribution quickly, we also get very close very quickly to the best we can do in terms of GROW. So that's very nice. So what does this look like in practice? It is, of course, a bit tricky to compare our sequential methods to an analysis with p-values. Because, yeah, with the p-value, you have to say before you start your experiment, I'm only going to look at time point 30, and then I stop. But with our experiment, you can say, okay, in advance, I plan to have money for 50 experiments, but I'm going to look in between and then decide to stop when my E-value exceeds 20. So this is why you see 3 lines in this plot. On the left side, by the way, you see the E variable used without any input from experts. And on the right, you see the E variable where we used knowledge about the odds ratio in designing the E variable. So there restricted this search space in the unit square. So what you see, the red line represents the number of samples you'd have to plan for with the p-value analysis with Fisher's exact test. And then in blue, you see what you would have to plan for with the e-value. So this is a bit higher. And then in green, you see what you expect to collect if you perform this sequential analysis and stop once you reach your threshold. So yeah, in practice, we expect to collect a similar number of samples or even a bit less, but you have to allot money for a lot more samples in advance. So this could be a disadvantage of this sequential setup for researchers. On the plus side, because of this validity in the sequential setting of the test, you're always allowed to start a new experiment or in case of futility, continue your study. And this is something that with the p-value analysis, you cannot really do. Yeah, so that might be an advantage. Okay, so now we tackled the testing part. So this was all about figuring out, is our point outside this gray dashed line? Is there a difference between the strategies? But now we want to extend this to estimating the effect and estimating confidence intervals. So what's the real problem here? We want to construct anytime valid confidence sequences that are valid at any time during our data collection. So we want to update our effect size estimates each time a new batch of data has come in. And we want to be quite sure that the real value of the effect size is somewhere in our interval, such that we not miss it. So formally, we denote this as we want a confidence sequence with a certain coverage. We want the probability that at any time point, the real divergence or difference measure between the parameters, that this is not in the confidence interval, has to be bounded by alpha. And here we use this delta to denote a measure of effect size. So as you might imagine, we just talked about the p-values where we only were allowed to look at one point. Otherwise, we would lose our type 1 error guarantee. And with classical methods, you also can't look at multiple times and construct your confidence interval, because then also you would lose your coverage guarantee. So what we can use here are the E processes again. But now we're going to construct them for a more general null hypothesis than the one where the parameters are just equal to each other. So we define a new E process for testing this more general null hypothesis with a parameter space defined by a certain effect size function. And I'll show you some examples on the next two slides. So the probability of falsely rejecting this null hypothesis is again bounded by alpha, because we have this E process still. And that is the trick why we can use it to construct these anytime valid confidence sequences. We include in our confidence sequence all values of the effect size function for which we have not rejected the null hypothesis. So for which our E variable was not surprisingly high. And this then gives us the coverage at the level 1 minus alpha we want. For example, 95%. If we again choose alpha to be 0.05. Okay, so our methods are really can really be implemented for any delta function you would like. But here are some examples again in this unit square. So for example, we could look at the risk difference. This is often something people are interested in clinical trials. Just the difference between the probability of success with my new treatment compared to the control treatment. And here, for example, you see theta 0 of delta, for delta, the risk difference measure, and the value 0.3. And then what we would do to look if it should be included in the confidence interval is perform a safe test with an E process where we test the null hypothesis that the true parameter lies on this green line. And when we then see a surprisingly high value, we can reject this null hypothesis and say, okay, I exclude this green line from the confidence sequence. We can also construct these null hypotheses in a different way. For example, here you see the odds ratio that looks like this. Yeah, and you can think of many more, of course. Okay, so yeah, we slightly changed the null hypothesis that we were testing. Luckily, it turns out that we still have a quite general expression of our E process. So here you see the E variable for observing this one data block. And again, we can multiply this to create this E process. And you see that it's only slightly different from the one I showed you before. But now we see in the denominator some other distribution that we have to find through minimizing some notion of divergence between distributions called Kullback-Leibler divergence. Some of you might be familiar with it. The details are in one of our papers, but the only key point of this is that for this expression to hold, we need this parameter space to be convex. And if this does not hold, the expression becomes a bit more intricate. You can also read the technical details of that in our paper. So for example, yeah, to deal with this convexity, I won't go over this because we are running out of time. So in some cases, only can construct one-sided confidence intervals, for example, for the logarithm of the odds ratio. So yeah, but I won't go over this in much detail now. I'll just show you what the confidence sequences look like. So this is a simulation for the risk difference. So as you can see, when we start our estimate, we have no idea. The real difference could be somewhere between -1 and 1. And as we then collect more and more data, we appear to converge to the true value. And what's also nice to see is that the true value of the difference between the distributions, between the success probabilities, is retained in the confidence interval. I also wanted to show we can detect very small differences between the groups as well. So I already mentioned for the odds ratio, we need this convexity criterion, and then we can only construct one-sided confidence intervals. So here you see a one-sided confidence interval where our maximum likelihood estimate of the true distribution lies here, and the green area indicates all points that are still included in this one-sided confidence sequence. And here you also see it for a smaller effect size. Yeah, so these were some nice examples, and now I'll get to wrapping up because it's really time. So to our knowledge, we've designed something that's quite new. So we've made a very flexible method in terms of block size, where the user can also choose their own notion of effect size that they want to measure. And that is also optimal in the sense of growth rate. So we expect to our evidence for the alternative hypothesis to grow as fast as possible during data collection. So this is quite nice. Yeah, something that already existed, for example, Bolt's sequential probability test, interestingly also turns out to be able to be interpreted as some kind of alternative E process or E variables. But those are different from the ones we designed, so they are not growth rate optimal. And they only allow for testing the odds ratio effect size. So we're still working on this subject matter. My colleague, for example, you now sitting there, he is working on investigating if this growth property also holds beyond the Bernoulli, or if you should use some other E variables in that case, for example, conditional E variables. And I'm also working on doing this research in subpopulations or stratified data sets and investigating conditional independence. And this is also something that I'm implementing at the hospital. We've also created an R package with a nice tutorial, which is called the vignette in the R language. And if you want to, you can try out these confidence sequences yourself and do some coverage experiments if you're interested. Yeah, so then I get to the end of my talk.
Thank you very much, Rosanne. So we still have time for a few questions. Here.
Thanks, Rosanne. So I think what you presented is a great tool for statisticians to have. I could also imagine, and I think you touched on it at the end, that you could achieve something similar with a mixture martingale. Like instead of estimating the unknown probabilities, you could use a mixture. Or you could use a Bayes factor. Do you have any idea of like, how do I weigh these different methods in my mind? What are the advantages that the E-value has over some of the MSPRT type tests or using Bayes factors? So I mean, under the alternative, I think you're using point estimates to estimate theta A and theta B, and there were different ways of doing that. And I think you had like the posterior mean as one way to estimate those. I'm also imagining that you could integrate those unknown parameters with respect to a prior distribution and use the Bayes factor. And I think this also gives a sequentially valid solution. But I guess I'm trying to weigh up the pros and cons of these two different methods.
You could do that. Yeah, what we do know is that we reach the growth rate optimal E variable, so the one that would have the lowest regret in the end.
Got it.
If we would really get to the true point. So if we get there fast, you'd expect to collect more evidence than when you keep using like a mixture indefinitely.
Right.
I think,
okay.
I don't know if
Yeah, thank you. So I actually think that it, if you mean what I think you mean, that it really doesn't make any difference in practice at all, at least for the Bernoulli model we tried. Because, yeah, we use the posterior mean, and because it's Bernoulli, the posterior mean, using the posterior mean, actually, if you multiply out everything, it's the same thing as using the Bayes factor. So I think that is just, and so it makes no difference. So that's if you use it in the graph, in the formula that Rosanne showed in the numerator, then it makes no difference, I think, for Bernoulli. Beyond, we don't know. For the denominator, you cannot do a Bayes factor because then you break the E variable property. So there we really have to do this, well, this formula that Rosanne showed. Yeah, so I guess that's probably, yeah.
Any other questions in the audience? No, I have one question. I was wondering while you were talking, is there anything known about the robustness to adversarial attacks for this sort of sequential decision making? Can you design, because you can make up a new A/B test at every point. Can you make up designs that will maximally worsen your estimates?
Worsen in terms of rejecting the null hypothesis or breaking the type 1 error?
Well, basically, I guess giving you the least amount of information, or
oh yeah, you probably could, but yeah, we will still have an E variable, so this type 1 error guarantee really always stands, as long as we really determine the block size before we start the data collection. But of course, you can get a really bad type 2 error guarantee. So if your estimate is way off, then you won't collect any evidence for the alternative hypothesis. Yeah.
Still fudge it. Any other questions? Because otherwise I would suggest to informally ask questions to Rosanne and also to Christina, of course. Thank you all. We will now have coffee and we will proceed in about half an hour.